Hello everyone, welcome to my video on rotational equivariant convolutional vision transformers. This video is recorded for a poster session at Eastern European Machine Learning Summer School. And this work is a part of an ongoing project with Google Summer of Code and provides preliminary results. A little introduction about me. I'm Kartik Sachdev, pursuing Masters in Robotic Systems at RWTH Aachen University, Germany. And my interest lies in self-supervised learning and reinforcement learning. Without further ado, let's dive directly to the poster. So in this work, the two different types of networks are combined, namely E2 stable convolutions and convolution vision transformers. And this way, it would induce rotational equivariance to a cyclic subgroup C4 in the transformer architecture. And the architecture was trained in self-supervised learning fashion on a highly symmetrical data set of simulated strong gravitational lensing images. And the model had an accuracy of 97% with only 65,000 parameters. So the problem statement. Strong gravitational lensing is a phenomena where the light from distance luminous object is bent and distorted by the gravity of massive foreground galaxy, which might contain dark matter. And a strong gravitational lensing is a method of detecting the substructure of dark matter halos. And the dataset consisted of simulated strong gravitational lensing images, which was generated using PyTorch, PyAutoLens library, and consisted of only 5,000 images of the images with and without substructure. So the implementation details. Basically, the E2 stable convolution block is placed before a convolution vision transformers, and to induce the inductive bias in the in the network before before the image is fed into the transformer block. And a single E2 stable convolution block consists the first stage consists of with the E2 stable convolution block, average pooling and global average pooling. And a convolution vision transformer consists of embedding layer followed by transformer where the multi-health self-retention is performed, and an MLP layer used for binary classification. So the intuition is to have the advantages of equivariant network and convolution vision transformers. With an equivariant network, we would be able to exploit the inherent rotational symmetries present in the data set. And with convolution vision transformers, we would have a shift and scale invariance, global context because of self-retention, and it has the ability to train on smaller data set. And this is the architecture which was proposed. The results and the future work. As mentioned earlier, the model achieves an accuracy of 97%, and which is only 1% less than our two-stage convolution vision transformers, but with a significant reduction of 86% in parameter count. And in order to check the rotational equivariance, the standard deviation of output lodges were compared, and the proposed architecture had only 0.48 the standard deviation, while CVT had a standard deviation of 0.96, showing a robustness to rotations. As this work is a part of an ongoing project and it provides preliminary results, there's a lot of scope of improvements. So the future work includes making the model equivariant under or E2C isosymmetries, that is translation, rotation, and reflection, and testing the architecture on bigger and different data set. And also, since there are a lot of versions of vision transformers, it would be interesting to see how can we combine equivariant convolution blocks with different versions of vision transformers. So that's it, and thank you for your kind attention.